My name is Dalen, and I'll be going over Lab 1, Constant Velocity. In this lab, the purpose is to compare the observed motion of some object that is moving at the same speed without changing direction to the predictions of its computational model. The fundamental principle that this law is about is Newton's second law, which relates the net interaction between systems and surroundings, the net force to the observed motion, change in momentum of system. Newton's equation is F net equals dp over dt, which is change in momentum over change in time. The formula can be manipulated thus that we can get the velocity update formula, shown right here. Moving on, I'll talk about experimental design. In my experiment, the system was the expo marker, the surrounding was a table on Earth, and the objective for this experiment was to determine the position of the marker over time and represent it graphically. This was done using these applications: computational, GlowScript, and experimental tracker. Now I'll be going over procedures of the experiment. First, we obtained the expo marker, meter stick, and something to record with. We placed the meter stick on the table, then record the constant rolling motion of the expo marker. We then imported the video into Tracker and analyzed the motion. We extracted the marker's position and corresponding time data frame by frame, then recorded these values in the provided data table. We created a computational model using GlowScript. We used the provided starter code template and modified the necessary values to calculate the predicted motion of the expo marker. We then entered the data from both Tracker and GlowScript into Excel, using this data to create a position versus time graph for both the observed and predicted motion. Lastly, we compared the two graphs based on our findings and drawing conclusions about how well the computational model predicts the observed motion. Here's my video of my experiment in Tracker. Notice, the red dots represent the position of the marker's center of mass in each frame. Here, the data is recorded in the table on the right, and this is where it's represented graphically. Calculations. With the data from Tracker, we put in the Excel sheet, and here I use to calculate delta t and v average. I use the second and third position and times. Here the delta t was 0.034 seconds, and we use the arithmetic average because f net was 0, which is final position minus initial position over delta t, which came out to be 0.79 meters per second. Alright, GlowScript. Because the net force is 0, the mass doesn't really affect final velocity according to the velocity update formula. I then plugged in delta t from previous slide, and here is the ending time when the marker hit the end of the meter stick. Again, f net here is 0. That's why this vector is 0. To calculate the final position, we have initial position, which was given from the previous slide, and then here is the final velocity, which is calculated up here, times delta t. Using that data, we plugged it into Excel, and here are the two graphs. Notice that as time progresses, the experimental data begins to deviate from the computational predictions. This discrepancy is due to experimental errors. Because the marker moved out of frame, I placed dots as close as possible to the video's border, which may have resulted in a shorter recording position than it should be. This could have introduced errors in my position tracking, affecting the graph data slightly. Additionally, external forces such as friction and air resistance were not considered in GlowScript's model, which may have contributed to the differences between the experimental and computational results. Lastly, rounding errors made while modifying the GlowScript code could have also affected the computational graph. Further questions. What if x and the negative x-axis were interchanged? The graphs would look the same, but flipped upside down. Instead of increasing position over time, it would decrease, meaning the slope of the graph would be negative. Second question, what does it mean? How many forces added to give 0 net force? If the marker's position is accurately predicted by the computational model with 0 net force, this suggests that all the net forces acting on it are balanced, such as gravity pulling down and the horizontal direction. Thus, the number of forces involved in creating a 0 net force could be 2, 3, or many more, as long as there are sum to 0 in all the directions. This concludes Lab 1. Thank you.